There are two definitions for acids and bases. The first one we're going to look at is called the Arrhenius definition. And this is similar to the definition that we used in our reaction chapter when we talked about neutralization reactions. So an acid is going to be defined as a compound that produces H+ ions in aqueous solution, and a base is defined as a substance that produces hydroxide ions in aqueous solution. So consider hydrochloric acid, HCl. When you put HCl in water, what happens is that the H comes and joins the water. You get H3O plus chloride ions. And so you get something called the hydronium ion. Now you might like to think about it as HCl breaks into H+ plus Cl minus. And that's just fine too. There are two different ways of showing the same thing, because the H+ and the H3O plus are really the same thing. It's just two different ways to show it. H+ will always join on a water molecule. It will never just sit there alone, because if you have this water molecule with the electrons here, the hydrogen's going to want to come stick to those electrons, making the H3O plus. So whether you see it H+, H3O plus, they're interchangeable. Now a base gives you OH minus. So, for example, sodium hydroxide can give you Na plus OH minus. And so these are all aqueous, and that's what makes it a base. These are also aqueous here, as all ions here are aqueous. So that's the definition of an Arrhenius acid and base. The acid gives you H+, the base gives you OH minus. Now it's important to realize that not every compound that has an OH on it can give you hydroxide ions. For example, alcohols have that OH, but it does not dissociate in solution, so it does not act as a base. The neutralization reaction for Arrhenius acids and base show that the H+ will combine with the OH minus to give the water molecule. And that's the neutralization that we've looked at before. So considering a double replacement type reaction, here we have NaOH. That's our base because it's got the hydroxide. So there's our base. The H is our acid. So in our double replacement, those come together and form water, and the other two ions, the Na and the SO4, form the salt. So our products are always water and a salt. Salt doesn't necessarily have to be NaCl, it's the ionic compound that's produced. Here's another example. This is acetic acid, so here's your H. And potassium hydroxide, there's your OH. Those come together to form water. And then the K goes with the acetate, so you have potassium acetate. So let's try these. You should pause it right here and do these on your own, and then you can start it again. So the H is going to go with the OH to give us water. And the calcium is going to go with the chloride. And when you put the calcium and the chloride together, you've got to consider their charge. Calcium is +2, chloride is -1, and so you've got to do the cross. So it's CaCl2 is your product. And now I'm going to erase those charges because you don't want to leave them in the compound because it's a neutral compound. And the water is liquid, and the calcium chloride is aqueous, so that's our salt. And to balance this, we have two hydroxides, so we're going to need 2 acids. We're going to get 2 waters, and that's that one. Looking at the next one, here's our H is going with the OH, so there's the water, H2O, liquid. And then the ammonium is going to go with the phosphate, NH4. And again, let's look at their charges. NH4 is plus, PO4 is 3 minus, so we cross those, and we want NH4, 3, PO4, and then erase those charges. And then this one is aqueous, and to balance it, we have 3 H's, so we're going to need 3 hydroxides, and we'll get 3 waters. So neutralization, it's the same as that we saw in the reaction chapter, and here they are written out a little more clean. The next definition is called the Bronsted-Lowry definition, and in this case, an acid is a proton donor and a base is a proton acceptor. So why do we say proton? When you consider hydrogen, remember it's a very simple atom. In the nucleus, it's got 1 proton, and then on the outside, it's got 1 electron. And that's what a hydrogen atom looks like. Now, if it becomes, so this is H, if it becomes H+, what happens is it loses the electron. So all that's left is 1 proton. So you can see that an H+ and a proton are the same thing. And that's why we call it a proton donor. A proton is the same as an H+. And really what's changing is the base is a proton acceptor. Hydroxide can take a proton, but there's other compounds can do it as well. So we're broadening our definition of what is a base, not just hydroxide, but anything that can take an H+. So let's look at this example. NH3, ammonia, is a good base. And it's not a hydroxide, but what you can see is that the H from the acid can go sit on those electrons, give us the NH4 molecule and the F-. Okay, so our acid is the thing that has the H. Our base is the thing that can accept the H. And the acid then turns into a base. And the base turns into an acid. Another thing to point out here is this double arrow. We haven't really used that before, but what that means is that the reaction can go both ways. The forward reaction happens, but the reverse reaction also happens. So this represents an equilibrium where the rate of the 2 reactions are equal. And you'll have some of the reactants, you'll have some of the products. Instead of just thinking of a reaction that all the reactants turn into products. Some reactions are like that, but many reach an equilibrium, and this is an example of that. In Bronsted-Lowry reactions, we have something called a conjugate acid-base pair. So here's another example of a Bronsted-Lowry acid and base. So here our base is the hydroxide ion, OH, and our acid is the ammonium ion. So an H can come off of the ammonium and join the hydroxide. And so what we've done is turned this base into water. So the base becomes a conjugate acid. And the acid, when we take the H off, it becomes the conjugate base. So the pairs are, we have OH minus, and that becomes H2O. And this is the base, and this is the conjugate acid. And you may not really think of water as an acid, but it can give hydrogen to become OH minus. The other piece we have is the NH4 plus is our acid, and it becomes NH3, and that is the conjugate base. So basically, you take the base, you add a hydrogen to make it the conjugate acid. You take the acid, you remove a hydrogen. So this one, you add the H+. This one, you remove H+. So let's look at a few more like that. So in these reactions, let's identify the acid, the base, the conjugate acid, and the conjugate base. So here's a good place to pause, see if you can do that. On our first one, the best thing to do is identify where's the H moving. So you look at your NH3 became NH4. It added an H. So this H right here is joining that. So the one that has an H and is going to lose it is called the acid. And the one that gains the H is called the base. So there's our acid and our base. Now the base becomes the conjugate acid, and the acid becomes the conjugate base. In the next one, we have the acetate ion and HCl. The H is going to come off of HCl and join the acetate ion. So the one losing the H is going to be the acid, and the one gaining the H is going to be the base. So here's our base. And then our base turns into the conjugate acid. I got too lazy to write out conjugate. And our acid becomes the conjugate base. Some compounds can be acids or bases depending on the reaction. Sodium hydrogen carbonate is an example of a compound like that. And sodium hydrogen carbonate is baking soda, so it's an interesting one to look at. Let's look at this first reaction. Is the sodium hydrogen carbonate acting as an acid or a base? Well, it looks like this H is going to come join the sodium hydrogen carbonate, and it will become H2CO3. So this one is our acid. This one is the base. Okay, and you might recognize hydrochloric acid, that is an acid. So when you put sodium hydrogen carbonate with an acid, it will be a base. And so the carbonic acid over here, that's what our base turned into. So this is going to be our conjugate acid. And this piece is going to be our conjugate base because the acid turned into there. Let's look at the next reaction where we're reacting sodium hydrogen carbonate with sodium hydroxide. And so now the H is coming off of the sodium hydrogen carbonate and joining the hydroxide. So sodium hydroxide now is the base, and the sodium hydrogen carbonate is the acid. So here we have this turns into, our acid turns into sodium carbonate, that's our conjugate base, and this turns into water, and that is our conjugate acid. So if you're in the lab, you may have noticed that sodium hydrogen carbonate is a safety supply that we have in the lab, and it neutralizes acid spills or base spills, so it's handy to have that in the lab. Here it is written out, if you couldn't read my writing on the last slide. What's the difference between a strong and a weak acid? And the difference is that strong acids are completely ionized in water, and weak acids are only partially ionized in water. So let's look at that. HCl is a strong acid, and so we use the one-way arrow. When we put HCl in water, it all turns into H3O plus or H plus and Cl minus. So if you imagine a beaker with HCl, so we put in HCl and we have water in here, it's not going to stay HCl. It's all going to split up to H plus Cl minus, H plus Cl minus, H plus Cl minus. So it doesn't stay together. It's 100% or completely ionized. Now, a weak acid only breaks up partly. So hydrofluoric acid is a weak acid. Notice we use the double arrow, saying that it will go to the products, but it actually doesn't go very far to the products. It's only about 1 to 3% goes to products. So not a whole lot goes to products. Most of it stays in the molecular form as HF. So imagine we had a beaker and we put into our beaker hydrofluoric acid, HF. What would happen is most of it stays together as the HF molecule. It's soluble, so it dissolves in the water, but only a very little bit will ionize to H plus and F minus, and most of it stays in the molecular form. So that's the difference between a strong acid and a weak acid. A weak acid is partially ionized, mostly stays in its complete molecular form. How do you know the difference between a strong and a weak acid? And basically we just have lists of these, and these are similar to some of the tables in your book. So you can use those tables in your book as well. Our strong acids are these 6: hydrochloric, hydrobromic, hydroiodic, nitric acid, perchloric acid, and sulfuric acid. There's not really much of a pattern to it. You just kind of have to remember them, put them on your index card for the test. The weak acids are hydrofluoric acid. Now notice hydrofluoric acid would fit in these categories. F is a halide like the chlorine, bromine, iodine, but HF is a weak acid. The next one is acetic acid, and that falls into a category of organic acids. And all of the organic acids are weak acids. So you remember those from the organic chapter. All of those that have the carboxylic acid group will be a weak acid. And then there's a whole category, I say most other acids, but all the other polyatomic ions, besides nitrate, perchlorate, and sulfate, the rest of those polyatomic ions, when they are bonded with hydrogen, make weak acids. So we've got sulfurous acid, carbonic acid, phosphoric acid, and most other acids are weak. So I recommend put the strong ones on your card or memorize them, and all the rest are weak. When it comes to strong bases, there's a bit of a rule. It's the soluble metal hydroxides. So you can use your solubility rules and look at the hydroxide. If it's soluble, it's a strong base. Now the exception is that ammonium hydroxide. Don't think about that as a strong base because it's not a metal. Ammonium is not a metal. So lithium hydroxide, sodium hydroxide, potassium hydroxide, strontium hydroxide, calcium hydroxide, barium hydroxide. Those are the strong acids. And the weak acids, these are the strong bases. And then the weak bases are, a lot of them are based on this ammonia molecule, the NH3. And remember how that has the N with the H, and these electrons. And that electron pair can attract a hydrogen. And so that's what makes that a weak base. And we saw that reaction. And related to NH3 is all the amines. So anything with an amine group on it is a base. Then there's a big category of salts of weak acids. And we'll look at these a little bit, but you may recognize this. It's close to H2CO3, but it's missing an H. So if it loses an H, and then you have HCO3 minus, okay, and that is actually a weak acid, so it doesn't do that very much. It actually wants the H back on it, so it wants to go this direction. So if there's H around, the hydrogen carbonate ion will snatch it up, and that's what you saw with the baking soda as well. So all the salts of weak acids are weak bases. We talked about electrolyte solutions. They're solutions that can conduct electricity, and here's the apparatus that you may have seen in the lab. So if you cut the wire to a light bulb and put the two ends of the wire in a solution, if the solution can conduct electricity, which is flowing electrons, then the light bulb will turn on. And there's really three categories. Strong electrolytes are solutions that contain a significant amount of ions and turn the light bulb on. This picture right here is a strong electrolyte. Non-electrolytes don't contain ions or contain almost no ions, and the light bulb doesn't turn on. And in between, we have weak electrolytes that have a few ions, and so the light bulb will turn on just dimly. So we can put different substances in these categories. So here's a table of electrolytes. What are the strong electrolytes? Strong electrolytes are things that create a lot of ions. So strong acids do, strong bases do. And we saw that because they're completely ionized. So if you put them in water, you get a lot of ions. The other kind of compound is soluble ionic compound. So if you put salt in the water, it will have ions in it and it will conduct a current. So these are the things that make strong electrolytes. Weak electrolytes are things that will put a little bit of ions, but not a whole lot. And so you can see that weak acids fit that category, and weak bases, because they ionize a little bit, but not very much. The other category that we have is slightly soluble compounds. And the rules don't really give you that much information on which is very soluble and which is slightly soluble, but some things will only dissolve a little bit, and you'll often know that because if you try to dissolve them in water, you'll see some solid left in it. Some of it dissolved, but not all of it, and some of those turn out to be weak electrolytes. Another one is dilute ionic solutions. Things like Gatorade. You need to replenish your ions, but if you drink salt water, that's not healthy. So it's very low concentration of ions, and many of our body fluids have that kind of dilute ionic concentrations, like normal saline that you might get if you get an IV. Then we get to non-electrolytes, includes pure water. Pure water does not conduct a current. Contrary to the tag on your hairdryer, pure water does not. Maybe conducts better than air, but you need some ions in the water to make it conduct. So pure water. And then the other category is soluble molecular compounds. These are things like sugar and alcohol and other substances that are polar, so they'll dissolve in water, but they don't form ions. And these will not turn the light bulb on at all.